Hello, and today is going to be a very exciting day because I get to talk to you about one of my most favoriteest topics, which is probability. And we're going to look at 4.2, 3, and 4 a little bit in this video. And then there's two example videos specifically talking about simple probability, the addition rule, which will be your ands and ors, and then also your if-thens that are in 4.4 and overlap a little bit into 4.5. But let's get a little background information about probability first. We're looking at the likelihood of an event happening. An event is the collection of results of outcomes from any particular procedure. So you roll a die, you flip a card. A simple event means that it can't be broken down any further, so you flip one card or you roll one die, or instead of looking at something like blackjack where you get dealt two cards, or in craps where you roll two die. The sample space is going to be the collection of all of those simple events, and that's normally where we start when we start to think about what is the probability of an event taking place. We need to look at the big picture first, see what all the things that could happen are, and then start to look at particular events. We'll use a capital P for probability, and you'll notice now until the end of the semester we'll see the letter P a couple of different ways. A capital bold P means probability. Inside of parentheses, sometimes they just say A, B, or C, but they could very well just write the event, so they could say the probability of event A, or they could say the probability of flipping a head or flipping a tail. And so we'll put it together like P parenthesis the event, either the event letter or the event name, and then close the parentheses. So if you see P of A, that means the probability that event A would occur. We can look at the probability of something happening as we do it, so that we'll complete an experiment and we'll look at how many times that event A happened out of all the times that we repeated the procedure. So for example, we can flip a coin 10 times, and so that would be my denominator because I flipped the coin 10 times. And then we can say, well, out of those 10 times, how many times did the coin land on a heads? And that would be my numerator. That's an experimental probability. In our class, and in most classes, you'll be looking at theoretical probabilities, which means if I were just going to do this endlessly, or even if you think about it as only doing it once, what's the number of different things that could happen over the number of ways that one particular event could occur? And so if I'm looking at a deck of cards and I want to flip over a card, there are 52 cards, so that would be the number in my denominator. If I want to look at the probability of specifically flipping over a jack, and there are 4 jacks in the deck, the probability of flipping a jack would be 4 over 52. Because theoretically, there's 4 cards that are jacks, and there's 52 cards in the deck. Now there's a connection between these two though, and that's called the law of large numbers. So as you repeat an experiment many times, and when I say many, I don't mean 10, I don't even mean 100. It could be thousands of times. Eventually that experimental probability, as you keep up like that running tab, will approach the theoretical probability. Now that doesn't mean that if you flip a coin 10,000 times that you'll get exactly 5,000 heads and 5,000 tails. It just means as you go over a period of time and keep repeating the experiment, those individual probabilities, that cumulative frequencies, are going to trend towards 50% of the flips heads and 50% of them tails. When we talk about probability, we can be a little sneaky about it. We figure it out as a fraction, as you saw in the previous slides. We tend to write it as a decimal, but then when we talk about it, we usually talk about it as a percent. So we're changing in between these 3 numbers, but those are just different ways to express the same probability. If we're talking about it as a decimal form, we're talking about numbers between 0 and 1, inclusive. You could have a 0 for a probability, and that means the event is impossible. It just absolutely cannot happen. And this does not happen a lot. There's not a lot of impossible events that we'll be calculating. If it's a 1, that means it's certain. It's definitely going to happen, and just like the 0, there's not a lot of certain events that are going to occur. Most of the things are somewhere in between those two. The closer you are to 0, the less likely you are. The closer you are to 1, the more likely that you are. And you can see even on here, we use our decimals, but you would most likely, let's say, like 50% chance or 50-50. We tend not to talk in decimals, but that's how we calculate our percents. Sometimes it's also easier for us to talk about the likelihood that it would not happen, because it would be less things for us to count up for our numerator. So the complement of the event, A naught, A with a bar over it, is that the likelihood or the probability that event A will not occur. So maybe I want to know the probability of not flipping a jack. Well, there's lots of cards in the deck that are not jacks. It would be easier for me to count up which ones are jacks and then say, oh, so the probability of not getting a jack is all of the other ones. And we can do this because they're disjoint. You can't be A and not A at the same time. It can't rain and not rain at the same time, unless you're in North Carolina, where it kind of feels like that sometimes. But these guys are disjoint, and so because one cannot happen at the same time as the other, the sum of those two probabilities has to be a 1. So what we saw with the jacks is that, well, what's the probability if I don't want a jack? The probability of something happening is for sure. I'm going to flip a card. So we can talk about that as 52 over 52. How many cards are jacks? Well, we know are 4. So the probability of getting a jack is 4 out of 52. So 52 over 52 minus 4 over 52 means the probability of not getting a jack is all of the other cards, which would be 48 out of 52. So maybe I really wanted to know the not, but there was just less of the jacks to count up, so I can save myself some time when I'm looking at whether or not I want something to happen or not to happen. We're not going to talk about odds. I'm just going to go right over these slides a little bit and start to talk about the addition rule. Because maybe you want a jack or a queen, or a 4 or a 5. When you have multiple things that will fill whatever need that you have for when you're calculating your probabilities, that's the addition rule. And then that becomes a compound event, because I'm going to take those two, or maybe even more, and add those two together. I'm going to merge those two together. So A or B in a single trial. So we'll take our probability for A happening, and we'll take our probability for B happening, and then we'll add those two together. But we have to look out for something that's called being mutually exclusive or inclusive. So we're looking for where the probability in A and B can both happen at the same time. With cards, we see this a lot. So maybe you want to know the probability of flipping a jack again, but maybe also a heart would be a good card. So the probability of flipping a jack or a heart, I would have to find the probability of the jack, which we know, 4 out of 52. Probability of flipping a heart, well, there's 13 hearts out of the 52, but I have one of those jacks that is a heart. And so he kind of raised his hand twice, and so he got counted twice. And so I'll have to count out that one extra by subtracting out the duplicate. Looks like this in my Venn diagram. Anything that winds up in the middle here is both in the yellow circle and in the pinkish red circle. And so that got counted twice, which is why I only have to subtract out that value once. That's when things are inclusive. A lot of things are mutually exclusive, which means you cannot have both at the same time. And there's a video up from Khan Academy where it talks about rolling a die, and so if you roll one die, and what's the probability that it's a 2 and a 6? Well, you can't be a 2 and a 6, and so that way that just wouldn't be possible. We can also talk about ands. And now this is going to be a little bit sneaky because we have ands and we have if-thens, But when we talk about them, when we don't have the symbols written down, they sound a lot alike. When you see probability of A and B, it means that we're going to either do them at the same time, like I flip a card over and it's a jack and a queen, or it can mean that I'm doing one and then the other, but they're two separate events and there's no overlap, so they're mutually exclusive. A good way to see what the relationship between those are is to create a tree diagram. So for example, if I have a 2-question quiz and I say the first question is a true or a false, and then the second question is a multiple choice with 5 selections. What are the possible permutations, right? What's the possible order of answers that you can put on this 2-question quiz? Well, I go to answer the first question, and I could put true or false, right? So you got to pick one answer. So let's say it's true, and then I move on to my next question, and I have to pick out of my 5 choices for my second question. So I can say true and then an A, true and then B, true and then C, and so on. But if I went to the first question and I decided, no, I think this is false, when I move to the same question for number 2, I can still pick A, B, C, or D. These guys are mutually exclusive. What happens on the first question has no impact on what's happening next. So how many different things could happen? 2 in the first, 5 in the second, and so that means I have a total of 10, and this is something called the fundamental counting principle. And it's a nice little shortcut to see how many groupings you have in your sample space. What we talk about more often than and, like having 2 things pop up at the same time, is an if-then. We'll use that bar in the middle. That means such that. And so that when you see P parenthesis B/A, that's the probability of event B happening such that A has already happened. So you want to look at this string of events, but you're going to assume that you get what you want on the first one. And we actually read this backwards. So it looks like B and then A, but it's really B given that A already took place. And so you'll do the event A, and then you'll move to event B. And in that moving to the second event, there may be an impact on what happened first on what happens next. And we'll see that a lot in cards, depending on the type of game. So if A and B are independent, they're very much like the 2-question quiz. What happens first has no effect on the probability of what happens next. So if I roll 2 dice, right? I pick up a die, I roll it, and I pick up a second die and I roll that. Or even if I pick up the very first one again. And we'll look at that when we play craps. More than likely, they'll be dependent, and this is what you see in card games. So when you play blackjack during your Chapter 4 quiz, when you get dealt the 2 cards, what card comes up first is going to have an impact on what could happen next, because you can't get the same card twice when you're playing with one deck. You'll use multiplication for this as well, because it's very much like the A and the B. But you'll have to, again, look for that overlap or that independence or dependence like you did with the ORs. And there is another video of A/B or B/A that goes through a couple of examples using cards. We're going to pause here, and then on the next 2 videos, you'll look at complements, conditional probability, and then also counting using permutations and combinations.